So the question says a cantilever shaft 50 millimeter diameter and 300 meters long. So diameter is 50 millimeters. This is the length. Has a disc of mass 100 kilograms at its free end. The Young's modulus, that is E, for the shaft material is 200 giganewtons per square meter. So this is your E value, Young's modulus. Determine the frequency of longitudinal and transverse vibrations of the shaft. So we have been asked to find the frequency for these two cases, longitudinal and transverse cases. Let's see. So longitudinal case is like this. Okay, here the mass, and for the transverse case like this. Okay, now first we have to derive the generic equation for this vibratory motion. Okay, so how to do that? We give a small displacement x, and here also we can do the same, and displacement is downwards, therefore x double dot, or the acceleration is also in that direction, and the restoring force is opposite to the direction of motion, therefore Sx, which is the restoring force, is acting upwards. So here it's the same, downwards you have the acceleration and upwards you will have the restoring motion. Okay, now let's derive. So the restoring motion, restoring force equals to the acceleration force, right? Restoring force is acting upwards and the acceleration force is acting downwards, therefore we can write this as minus Sx equals mx double dot. Okay, therefore x double dot equals minus s over m into x. So in this equation, s over m term is what? S over m is the omega n squared, therefore omega n is s over m squared. Now if we know the angular velocity, we can determine both the time period as well as the natural frequency. How to do that? We know that t, or the time period, equals 2 pi over omega n. So here time period is MOS. This is the time period, and the natural frequency is 1 over t. So this is the natural frequency. Now this is the expression that we derived for the natural frequency. Okay, and we can further simplify this one by considering the equilibrium state of the system. So before we give the displacement of x to this system, it is in equilibrium. Okay, the mass is balanced by the upward force acting due to the mass is balanced by the restoring force at the equilibrium state. So here delta is the static deflection of the system, of the shaft. Okay, so we can write an expression for S over M. S over M equals G over delta. Okay, S over M equals G over delta. So we can substitute it in here, G over delta. Okay, now we know the value of G, right? G is 9.81. Then we know the value of pi as well. Therefore, by substituting these values, we can get a relationship. It reduces to 0.4985 over square root of delta. Okay. You don't need to memorize this, just derive these, and you can use this expression to determine the Fn value, or the frequency, natural frequency, for the longitudinal and transverse cases. Okay, (0.4985 over delta). Okay, so for the longitudinal case, delta is equal to WL over EA. Here W is the force, L is the length, E is the Young's modulus, and A is the area of the constraint. Okay, and so for the W it is mg, L is given 300, E is given 200. A, how to calculate A? A is the area of the constraint, so 5d squared over 4. 5d squared over 4. For the transverse case, delta, or the static deflection, equals to the W into L to the power of 3 divided by 3EI. This one, W is the force, L is the length, E is the Young's modulus, and here I is the moment of inertia of the shaft. It is pi over 64 into d to the power of 4. Okay, pi over 64 into the d to the power of 4. So by substituting the given values and calculating both A and I, you can find the frequency of these two cases. Okay, so when it comes to mechanical vibration, you should know the types of spring configurations. So there are mainly two types of spring configurations. We can categorize these two as series and parallel. Okay, now series configuration, if I were to depict, so it could be something like this. So here I have a spring mass system which has two springs, this one and S2 are the two stiffness values of these two springs, and this configuration is of series type. So in series configuration, so how to identify a series configuration? In a series configuration, if the deflection of the system is x, let's say the deflection of the mass is x, then it is equal to the addition of individual deflections in each springs. For an example, if the deflection of the first spring is delta x1 and the deflection of the second spring is delta x2, the addition of these two deflections would be equal to the deflection of the system. Okay, so how to find the equivalent stiffness value? It is denoted in SEQ. So this is like the capacitors. Okay, how to get the equivalent capacitance in series configuration? So it is equal to 1 over SEQ equals to 1 over S1 plus 1 over S2, and SEQ, or the equivalent stiffness value, is 1 over S1 plus 1 over S2. Okay, so this is the method to find the equivalent stiffness value when there are two springs. If there are more than two springs, then you can use the same method to find the equivalent stiffness value. Let's take a look at parallel configuration. So in this case also, I've taken a spring mass system having two springs, S1 and S2. So in a parallel system, the deflection of the system equals to the deflection of each spring. For an example, if the deflection the S1 spring is delta x1 and the deflection of the second spring is delta x2, then the deflection of the system, that is x, equals to the deflection in each spring. So it is equal to delta x1 and delta x2. Okay, so both the springs deflect by a distance x. Okay, so in order to find the equivalent stiffness, you can simply add the two stiffness values. Okay, so here this is the equivalent stiffness value of this system. Okay, and so this is one configuration of the parallel system, and there is another configuration. So if you have a spring mass system like this, okay, and you deflect this mass m, you displace this mass m by a distance x, then what would happen? The S2 spring will compress, right? It will compress by a distance x, and the spring S1 will elongate. Okay, will elongate means the length of that spring would increase by a distance x. So therefore in this case also you can find the equivalent stiffness value of the system by using this relationship. You just add the two stiffness values. Okay, take a look at this example question. So here they ask us to model the system shown in figure by a block attached to a single spring of an equivalent stiffness. Okay, so they are asking us to find the equivalent stiffness of this spring mass system. Okay, so here first of all we need to categorize these spring configurations into series and parallel. So here this one, as you can see, these two are in parallel configuration, and also these two are parallel. Therefore we can get the equivalent stiffness value of these two by just adding the two stiffness values. So here we get 2k plus k, we get 3k. In this spring configuration also we have a parallel system, and the equivalent stiffness would be 3k. Okay, and now okay, let me draw this. Okay, now as you can see, these four springs are in series configuration and these two are also in series configuration. So we can get the equivalent, I'll take this as K1 equivalent and this one as K2 equivalent. So K1 equivalent would be 1 over 3k, and as you can see there are 3 springs having a stiffness of 3k, so we can simply multiply this by 3 and this guy 1 over k. Okay, and 3 cancels out, and this is k over 2, and this guy you can write as 1 over k plus 1 over 2k so it becomes 2k over 3. Okay, 2k over 3. Now let me draw our system again. Now it is like this. K over 2 and 2k over 3. We can further simplify this one. So they are asking us to model the system by a block attached to a single spring. So as I mentioned in the theory part, this is also a parallel configuration. Okay, this is also a parallel configuration. We can find the equivalent stiffness by simply adding these two stiffness values, right? K over 2 plus 2k over 3, and now the equivalent stiffness value is 7k over 6, and we can draw the final system as this. Okay, so this is your final system with a single block attached to a single spring, and the equivalent stiffness value of this spring is what? 7k over 6. Take a look at this example here. In this case also we've been asked to find the equivalent stiffness of the system, and so this is an interesting case here. Apart from normal springs, we have a beam attached to this system, right? So in this case also this beam also has a stiffness value, right? And so how to find the stiffness of the beam? Okay, so as you can see, this beam is a cantilever beam where one end is fixed, and a concentrated load is acting on the free end, right? So for this type of a beam, we can find the stiffness by using this relationship 3EI divided by L cubed. Okay, we can find the stiffness value of this type of a beam by using this relationship 3EI over L cubed. Okay, so here, since we don't know the value of the concentrated load, we can treat it as a unit load. Okay, here E is given, I is given, and we know the length of the beam as well. Therefore you can calculate the stiffness of the beam. Okay, now as I mentioned in the previous example, we need to categorize these things, these given spring configurations into parallel and series. Okay, so as you can see, this top spring and this beam here. Okay, so I will take this as S1, S2 and S3. Okay, so I will remove this beam and the upper spring so that you can get a good idea about the system. So like this. Okay, and let's say a concentrated load is acting downwards at this free end. So what will happen is, if the load is acting downwards, what will happen is this beam would rotate like this, right? This beam would rotate like this. Let's say the small angle is theta, it is rotated by a very small angle theta. Okay, and now, so what is the deflection of the beam at this free end? Deflection of this beam at the free end would be L theta, right? L into theta, because the theta is very small, we can write it as L theta. That is a deflection of the beam at the free end. Now, since the free end of this beam is attached to this upper spring, the upper spring would also elongate from the same amount. Okay, so the displacement of the upper spring would also be L theta. Okay, so since the deflection of the beam is equal to the deflection of the upper spring, we can consider these two as a parallel arrangement. Okay, as a parallel arrangement. So okay, Now this is I will take this as SB. These two are parallel. Now I will redraw the equivalent system. Now I'll redraw the equivalent system. SEQ1, here S2, and here you have S3. Now SEQ1 equals to, so since these two are in parallel mode, you can simply add the two stiffness values, right? Now we can further simplify these. These two springs are in series arrangement, so we can further simplify this as a two spring system like this. Here you have S3 and here you have SEQ2. Okay, these two are in series mode. Okay. And again, you can further simplify this to a single mass spring system like this. Why? Because in the last section I mentioned, if you have an arrangement like this, the deflection or the displacement of both these springs would be equal to the displacement of the system. Therefore, this is also a parallel arrangement. By adding these two values, these two stiffness values, you can find the equivalent stiffness of the system. So all the values are given. You can try this on your own. Take a look at the question given. A machine part is modeled as a pendulum connected to a spring as illustrated. Ignore the mass of pendulum's rod and derive the equation of motion. Then after that, linearize the equation of motion and compute the formula for the natural frequency. Assume that the rotation is small enough so that the spring only deflects horizontally. Okay. Now initially the mass which is attached to a beam of length L is at this position, vertical position, and there is a spring attached to the mass. So what they have done is they have given a small angular displacement theta, and the direction of theta is what? It is in counterclockwise direction. Therefore, theta and theta double dot both are in this counterclockwise direction. And if we draw the mass now, so what are the forces acting on the mass? So at this instance, you have mass acting, so the weight acting downwards, and there is this string tension of the spring, the restoring force of the spring. So I will denote it as Fs, right? So in order to derive the equation of motion, so the easiest way that we can get the equation of motion is by taking the moments about point O. Okay, so as you can see, if we take the moments about point O, then we will only be getting expressions from the mg term, which is the weight of the of this attached mass, as well as this restoring force of the spring. We won't be getting any t term when we are taking moments about point O, because t goes across point O, right? Therefore, we can write the moments equal to I alpha, the sum of all the moments equal to the moment of inertia into the angular acceleration. So first let's write the moment from the mg term. It is mg into this distance. That distance is L sine theta. Now take a look at the direction. So the moment caused by mg is in the clockwise direction. Therefore, we denote it in negative sign. Okay. Then we have the restoring force of the spring. So Fs is what? The restoring force is here the stiffness of the spring is given as K and into the displacement of the spring. So what is the displacement of the spring? It is L sine theta. L sine theta is the displacement of the spring, and that is the value of Fs. Now let us take a look at the moment generated by this Fs. So it is Fs into L cos theta. Fs into L cos theta. This distance would be L cos theta, right? Therefore, Fs into L cos theta. Fs is K L sine theta, then into L cos theta. On right hand side you have I, and we know that for a case like this, where a lump mass, where a mass is attached to a string or a rod, the moment of inertia is ml squared. Okay, moment of inertia is ml squared. Then you have theta double dot. So L is common, we can remove one L from both sides, and we get theta double dot equals, here you have minus mg sine theta plus kl sine theta cos theta now we can get theta double dot equals minus mg sine theta minus kl sine theta cos theta divided by ml. Okay, now we have been asked to linearize this equation, and they've asked us to assume that the rotation is small enough so that the spring only deflects horizontally. When the theta is so small, means it is when it is closer to 0, we can assume that the spring only deflects horizontally. Okay. When theta is going to 0, we can take sine theta as theta, and cos theta goes to 1. Okay. Now here we can further simplify. Minus mg theta KL theta divided by ml. Theta dot minus, we can take theta out, mg plus KL over ml theta. Okay, now so this is a familiar equation to you, so it looks like this, right? Therefore the natural angular frequency is what? The square root of mg plus KL divided by ml. Okay, now this is the answer. Now in this example we have a simply supported beam, and as you can see, this spring mass system goes right in the midpoint. Okay, goes right across the midpoint of this beam. So like what we did in the previous case, this beam, this simply supported beam, has a stiffness value, right? And in this one, since it is the system is attached at the midpoint of the beam, we can find the stiffness value of the beam. I will take it as SB by using this relationship 48 EI over L cubed. Okay, so you can use this relationship to find the equivalent stiffness value of a simply supported beam at its midpoint. Okay, now just like in the previous case, in this one also, this beam and the upper spring forms a parallel spring system. Okay, forms a parallel spring system. Therefore we can simplify this system as I will take this as SB, S1, S2, S3. Okay, now I can simplify this thing as I will take this as S equivalent 1, then S2, here we have our mass, and S3. Okay, now S equivalent 1 would be SB plus S1. Why? Because these two form a parallel system. Okay, now what about these two, SEQ1 and S2? These are in series mode. Okay, and I can further simplify this system as S3 and S equivalent 2. So here S equivalent 2 is simply what, 1 over S equivalent 1 plus 1 over S2. Okay, and finally again here we have a parallel system. We can simplify this further to a single spring, single mass system like this. Okay, is equivalent 3, and here the equivalent stiffness of the system can be written as S equivalent 2 plus S3. So this is the final or the equivalent stiffness of the entire system, right? So all the values are given here. So if you plug in these values correctly, you should get the answer as 3.47 to the 10 to the power of 5 newtons per meter. Okay, so this would be your answer. They're asking us to find the natural frequency of the 200 kilogram block. Natural frequency. So you know the relationship between the natural frequency and the mass and the stiffness of a system. So natural frequency equals to the stiffness of the system divided by its mass. So here stiffness is what? We just calculated the stiffness, 3.47 10 to the power of 5, and the mass is 200 kilograms. Okay, then the answer for the natural frequency of the system is 41.6 radians per second. Okay,